Okay, guys, I'm just going to go through this note here. This is, let me change that up. Days 4 and 5 from Unit 4, sorry. And this is 4.3 binomial distribution. So I have my note from class this morning. I'm just going to use this. It's very colorful. And what we're looking at here is binomial distributions. So binomial distributions, we start off by looking at an example here where we're rolling dice, a pair of dice, and we're looking to find out to see if we have rolled doubles or not. So use the highlighter here. And we go through here and we draw the first trial. Is it double or not double? So D prime or D complement here. And the odds of rolling a double are 6/36 or 1/6, and the probability of rolling not a double is 5/6. So each of these branches is identical, okay? And we draw these all the way through, and then we have all three trials. Okay, and then what I've done here at the end I follow this branch and I say, okay, how many doubles do I have here? How many D's do I have here? Well, I have 1, 2, 3 doubles. And then over here, I follow this one and I have 2, and this one was 2, and then I just noticed that is 2 also, and I'm just going through it. This one was 1, just that. That's a prime, that's a prime. So no, 1, 1, and then finally, zilch, none. Okay, and when you look at that, so that's all the different ways to roll 2 dice and figure out if you have doubles or not. So you can either have 0, 1, 2, or 3 doubles, like we just said. And then if I go back, I want to see how often do these things happen. Okay, how many terminal branches? I'm ignoring the probability for a second here, but I want to figure out how many terminal branches end or have 3 doubles, 2 doubles, 1 double, or none doubles. None doubles? No doubles. Okay, so here I just have the one branch that ends in 0. Okay, so how many branches have 0? It's just the one. There's 3 different branches. If I go back in the light blue, there were 3 that have 1 double, 3 that had 2 doubles, and 1 that had 3 doubles. And then I went back in class and I looked through this and I said, look, if that happens like that, what do you think would happen? Let's go backwards and let's pretend we just had an experiment that looked like this, and we only had two rolls of the dice. How many different results can you have? You could have no doubles once, you can have 2 doubles once, and you can have 1 double twice. So you could have 1, 2, and 1 result. We just had 1, 3, 3, 1, and if you look at this, it turns out to be, this kind of duplicates Pascal's triangle. Anyway, that's the number of ways you can get these results. Okay, 1, 3, 3, 3, 1. There's a pattern to it. And then we talk about the probability of this occurring. We just follow the branch all the way through. So if I was to say, let's just look at this one right here. What's going on here if I have 2 doubles? Okay, so if I have 2 doubles, that can happen once, twice, 3 different times. And for each of these to have 2 doubles, you have a not a double here, so 5, 6, and then you have a double, which is 1, 6, and a double, which is 1, 6. So to find the probability of that occurring, it would be 1, 6 times 5, 6 times 5, 6, which is the same as 1, 6 to the power of 1 and 5, 6 to the power of 2. And that's the probability of that occurring. Okay, and then if you multiply that by the number of ways it occurs is 3, the overall XPX is 75/216. Anyway, I'm probably confusing right now, but let's continue here, and then we'll make sense of this whole thing. What I'm trying to do is develop the formula, and the formula is this: the probability of something to occur in a binomial distribution. So let's stop for a second and consider what a binomial distribution is. A binomial distribution, a binomial situation, is when there are independent trials. Okay, so there are trials. So rolling the dice, independent. Remember, with independent, you roll the dice, you get a result. You roll the dice, you get a result. You roll the dice, you get a result. One result doesn't influence the other. So they're independent trials. Okay. And in each independent trial, there are only 2 events. There's success or failure. That's it. That's all we're going to have. Okay, there's not 3. We're not doing a situation where your cat can have 4 different colored fur or whatever. It's just yes and no. Success, failure. That's it. So binomial distribution, independent trials, success or failure. And we look here and we call X the random variable, and it represents the number of successes. If that is the case, the probability of X successes is N, choose X, P to the X, Q to the N minus X, where P is the probability of success and Q is 1 minus P. Okay, so if that didn't confuse you, let's go back and make sense of what's going on here. if I want to find out what's the probability of rolling any of these, let's just go rolling one double, okay? One double out of 3. How to get this is you're going to use your old friend choose, and if we're rolling 3 times, right? We roll 3 times. I want 1 success. So the 1 is the x is the number of successes. So see here, I had an x. I don't know if you can see that anymore, but that's a 1. So I go P1 is equal to 3C1. Why 3C1? 3 trials. That's my n, number of trials, and I want 1 success, which is x. P is the probability of success, and we said that success is rolling a double. We've defined it that way. And there's a 1 in 6 chance of rolling a double. How many times do I want that to happen? Just the 1, right? Because that's what I'm figuring out here. P1 is 1 double, okay? And then that means if I succeed once, I fail twice. Okay, so that's all we can do in this part of the course is succeed or fail. That's it. Okay, so if I wanted to figure out what's the probability of 1 double, that's 1 success out of 3. So 3 trials, 1 success out of 3. 1 out of 6 to the 1, 5 out of 6 squared, and I have to go 3C1. Okay, and then what happens with that? I just work that whole thing out, and I end up with the probability of 3 times, and that's going to be 25 over 216, and so this, hold on, let me just switch this up. And that's going to be 25 over 216, and that's going to be 75 over 216. So the probability of rolling exactly 1 double out of 3 chances is this right here. Kind of ugly, but you'll see when we do the next example, it's kind of useful. If you want to get the expected value, you can just do the sum of the xpx's like we did in the past, or we can do this. So we can make a table here. I did this morning. You can make you can add to the table an xpx column here, like we did with the uniform distribution. So what happens here is you take this number here and take it and multiply by all of this to get 125 2/16. Okay, and then and then you multiply this by 0, and then you multiply this by 1, and then you multiply this by 2, and then this by 3. So take the probabilities and multiply them by the x's. Okay, so actually I didn't make that table. So you would do that, multiply these out and get totals. And what you can then, so over here, it's 0 times the probability of 0, 1 times the probability of 1, 75 over 216, 2 times 15, no, I think it's 25 over 216, and 3 times that, and the whole thing turns out to be a half. Okay? Easier way to do it, though, if you know it's binomial, all you do is the expected value of the experiment is the number of trials times the probability of success. So if I have 3 trials, right, 3 flips, and I have a 1 in 6 chance of success, all I do is multiply 3 times 1/6, and I still get 1/2. So easier way to do it, EX equals N times B. Okay, so that's easier. Now let's look at this situation here. We had this morning. I did this, and I'll do it in the afternoon too. People with the left thumbs overlapping on top of their rights. Put your hands together, and if your left thumb is on top of your right, the probability of that happening is 55%. The probability of your right thumb being on top is 45%. We're going to call left thumb success. So this is success, and this is failure. So here we're going to say let x equals the number of left thumbers, and success will be 0.55, and failure will be 1 subtract 0.55. So where do you get these numbers from? This is just from over here, and even though that we're already given this, we also could do it this way and say 1 subtract 0.55 is 0.45. So if we want to look at this situation here, and we can make a whole chart here, but let me do a different question here. Let me just ask you this: what are the odds? What's the probability? I'm not even going to do the question we did in class today, but let's look at this. Let's say I have 22 people in class, okay, and I want to figure out what is the probability that, I don't know, 7 of them, exactly 7 of them, are going to be left thumbers, we'll call them, okay? So people who have their left thumb on top of their right thumb when they close their hands. Well, what I want here is we're going to call left thumb success. So of the 22 trials, we're going to have 7 of them be successful. And what you do here is you multiply the percentage, or the probability of success 0.55, not the percentage, but the probability of success 0.55 by the number of successes, which is 7. And then failure occurs 45% of the time. If we have 7 successes in 22 trials, 22 subtract 7 is 15. That means we have 15 failures. Okay, and again, don't get all excited about failure and success. You kind of math words. These are people who normally don't have healthy relationships with people, so they can use words like failure and success and not offend anybody. But that's kind of how we talk about it in math. So 22, choose 7. Don't forget what that is, as I write over this child's hand. 22 factorial, and that's going to be 7 factorial and 15 factorial. So figure out what that is, and then 0.55 to the 7 and 0.45 to the 15. Work that out and get a number. Okay, so that's the probability of getting exactly 7 people. Now, if we were to do the same thing with 22 people, once again, and I wanted to know what is the expected value, how many people of the 22 are left-handed, well, let's just use some common sense, first of all, or left-thumbed. 55% is just more than half, so our answer should just be more than half, so something like, I don't know, 12 should be our answer. So let's see if that makes sense. If we just look at this right here, EX, that's an E. My E's look like a sigma, so I want to be careful. You can go ahead and work this sigma x px thing out, but even easier if you know it's binomial. You just say I want there are 30 trials. Sorry, 22 trials, right? 22 kids being checked, and the probability of success is 0.55, and then you're going to multiply that out, and I think what's that? That's 11. I think that is actually 12.1. So 22 times 0.55 is 12.1. So that's your expected value. So in 22 kids, a class of 22, if I asked how many people are left-thumbed, the answer should be 12.1. Okay, let's keep going and do a couple more if we have time. So I did it a little different here. And then we did a histogram in Google Sheets, and we can continue here. So Circumdy claims that every box of their raisin buds has at least 100 raisins. I don't want to say Raisin Brand because I don't want to get sued. A recent test shows that 8% of boxes contain less than that amount. Oh, that's sad. If this is true, what is the probability that at least, if we test 20 boxes, that all 20 boxes will have more than 100 raisins? So these guys are saying 8% of boxes don't have the right amount, and we want to figure out what happens if I take 20 boxes. So what's the probability that if I check 20 boxes, that all 20 will be okay? So if we want 20 boxes on the nose, let's change this. Let's pretend we said at least 19 boxes will have more than 100 raisins. Okay. So one way to do that is at least 19 boxes would really be 20 boxes or 19 boxes. Okay. So what we do is we find the probability. What we're going to do is find P19 and add to that P20. Now, what we have to do here is define what success is, because in this case, we're going to consider success having a lot of raisins. Okay, so if that's the case, if we say X is equal to greater than 100 raisins, if that's the case, then we're going to have P as 0.92 and Q as 0.08. Now, where did I get that from? 0.08 is how many 8% of the boxes had less than 100 raisins. So if that's the case, that's failure. And then if that's 8, then this has to be 92. 92% of the boxes have to succeed. Okay, so if we're going to do these, what we do here is that's going to be out of the 20 boxes, we want 19 to succeed. And if that's the case, we want, of the 20 boxes, we want one. Sorry, let me redo that here. Of the 20 boxes, you want 19 to be successful. And if 19 are successful, well, because we're doing binomial here, 92% are successful, 19 are successful. So you put the number of successes, this is success percent, times 19, which is the number of successes, and 8 are failures. And what you would add to that is the probability of 20, which is this, 0.92, 20, 0.08. Nope, that's an 08.